This is section 3.4, and this section is going to be on linear inequalities. These are going to be sort of similar to the linear equations that we've solved in the past, but these are not equal. Right? So instead of an equation, we're going to have these inequality symbols. So just a quick review of the inequality symbols that we're going to be working with here are these. The trick to remembering less than and greater than is that less than kind of looks like the letter L. That's how I always remember the difference there. Okay, so we need to get some stuff out of the way, some terminology before we get into the inequalities. So let's get some stuff out of the way here. A set. A set is just a collection of objects. Okay, it can be numbers, it can be symbols, it can be people, it can be animals, letters, whatever. The things in the set, these objects, are called elements. So if I write set A is made up of the numbers 2, 4, 6, 8, 10. This A is the set name. This little brace, those little symbols right there, are what lets you know that it's a set. And then the numbers in that set are called elements of the set. We say that there are 5 elements in this set. 1, 2, 3, 4, 5 things in that set. Now, set B here is slightly different than set A. It looks very much the same. The only difference is these ellipses here. Now, this suddenly makes this have how many elements? Well, it's not 5 anymore. In fact, now there's an infinite number of elements because this symbol right here is telling you that this pattern continues on forever. So we say that this set is infinite because it has an infinite number of elements. Set A was finite because it had a finite number of elements. Now that doesn't mean that ellipses always mean infinite. So let's take examples, or this one, set C for instance. These dots right here, that's telling you that this pattern continues from 4 all the way up to 50. This is just an abbreviation so that we don't have to write all the numbers from 4 to 50. But it's still finite. This has 50 elements in it. So ellipses on the end, yeah, that means it's going to be infinite because it continues forever. But in the middle, it's going to be a finite set there. Now, a set can have no elements in it whatsoever, in which case it's called the empty set. So we can write the empty set 2 ways. We can either write it as a set with these little braces with nothing in it. Nothing. I mean, not a 0, not a symbol, nothing, just air. Or we can write it without the braces and just write a circle with a slash through it. Don't combine these into one symbol. If you do, it's no longer the empty set. So if you try to put this symbol inside there, totally different. Okay, that means that's an element with one set. Now, also, if I put 0 in here, some people think that's the empty set because they're like, oh, it has nothing in it. 0 is nothing. Well, no, that has one element in it. It's got 0 in it. So, all right. Let's talk about unions and intersections. The union of 2 or more sets is denoted with this little U, but it's not like a capital U, so it doesn't have that little leg to it. It's the set of elements that are either in A or B or both. The intersection is the overlap. It's the stuff that's in both A and B. Right? So visual for that. If you have circle A here representing all the stuff that's in A, and then you have B representing all the stuff that's in B, this bit right here is the overlap. That's the intersection. That's the stuff that's in both circle A and circle B. This over here is the union. It's the stuff inside circle A and inside, or inside circle B, or inside both. Okay? Now, I don't want you thinking that these two are like opposites of each other or anything. The union actually includes the intersection. Okay? All right, so let's do some examples. So given that set A is made up of the elements 1, 2, 3, 4, 5, 6, and set B is made up of the elements 1, 2, 5, 7, 10, let's find the intersection. That's the overlap of these sets, okay? So what numbers are in both A and B? That's the intersection. So you should pause the video, figure out what numbers are in both A and B. All right, so the intersection are the numbers 1, 2, and 5. That's the numbers that are in both. Don't write it twice. Don't write 1, 2, 5, 1, 2, 5. You only need to write the numbers once. The union is made up of everything in A along with everything in B, including anything that's in both. So here's how I did the union. All right, I just smooshed the sets together to start with. So I just wrote set A, 1, 2, 3, 4, 5, 6, comma, and then just started writing set B, 1, 2, 5, 7, 10. That's going to be the union smushed together. Now here's what you got to do. You do have to omit any repeated elements. So like 1, oh, I already wrote it. 2, oh, already wrote it. 5, already wrote it. So I'm just going to scribble those out. That means my union is actually 1, 2, 3, 4, 5, 6, 7, 10. So just don't write those. But that's an easy way of doing the union, right? Just smush them together and scribble out any repeats. All right, this next example looks a little scarier here. So M, this is in what's called set builder notation. This is read X such that X is greater than or equal to 5. So this is just like that super sexy math way of saying all the numbers that are bigger than or equal to 5, right? That's all the integers here, bigger than or equal to 5. This is everything less than 12. So this is what's called set builder notation. And here's how we're going to read it. It is read the set of numbers, and that little line right there represents such that this happens, those numbers that are greater than or equal to 5. Now, I did say integers, and I misspoke there. It's any number, because it doesn't say. Sometimes it'll say in here where X are, specifically integers or whole numbers or anything like that. And yeah, I misspoke about that. So if we're going to find the union, the intersection, this is on a number line. So instead of using the circles like I did last time, this time we're going to use a number line, because those are going to be a lot more common with these inequalities. Okay, so here's what I did. This I did in red. Okay, this M. So where are all the numbers that are greater than or equal to 5? Okay, well, here's 5 on the number line. Everything greater than is going to go to the right, because we know on a number line all these numbers are bigger. Everything less than 12, remember the less than looks like an L, less than 12 is everything from 12 back to the left, that's less than. Now notice something here. Notice that on 12 I put a parenthesis, and on 5 I put a square bracket here. Why did I do that? Well, the parenthesis goes with what we call the strict inequality. That's the one that doesn't have an or equal to. If it has an or equal to, we put a bracket on there. So there's a lot of these little tiny rules in here, but that's just to differentiate between the two. So the stuff in blue is this set. The stuff in red is this set. So where is the union and intersection? Well, let me do the intersection first. The intersection is the overlap. So the intersection is anywhere that's shaded both red and blue. Well, that's this middle part right here, and that's everything from 5 to 12. The union is anything shaded, period. Remember, the union is one or the other or both, so it's blue or red or both. And it just so happens on this particular example that everything is shaded in either blue or red or both. So we say that the union is everything, and we write that with this negative infinity to positive infinity. This is what's called interval notation. All right, so the stuff that I just said, the intersection there is that 5 to 12 interval, or you can write it in this set builder notation as X such that X is greater than or equal to 5 or less than 12. I prefer interval notation to set builder notation just because it's a lot less to have to write and I'm lazy. So, the union was everything. You could write the set builder notation like that, where x such that x is any element of the real numbers. I don't know if you guys have seen this symbol before. That's the symbol for all real numbers. It's a little double-legged R. And this little e right here means is an element of. So that's what all that means. Okay, so just to recap where we're at. Those are called parentheses, these are called brackets, and those are called braces, the little curly things. There are 3 different ways to write sets. Okay, we got the set builder notation, which is, the really messy, convoluted looking one. We can write it in what's called an inequality notation. I think Hawks calls it algebraic notation. That's where you just drop all this mess over here and you just write the inequality part. Or you can write it in what's called interval notation. So this means the interval from 5 to infinity. Now, for interval notation, I mentioned this earlier. How do you know when to use a parenthesis and when to use a bracket? Well, the strict inequalities, that means strictly less than, strictly greater than, no or equal to. For the strict inequalities, we're going to use parentheses. For the or equal to's, we use brackets. This is going to come up again later. Let's see, when do we do this again? That whole, or the strict inequality or non-strict inequality, I think it's going to show up again like in 4, 6, 8, 8, somewhere in there. So let's talk about interval notation here. X less than 3. That means everything less than 3. Oops. Finish that out here. Okay, so on a number line, I just put 0 there for reference. There's 3. Less than 3 is to the left of 3. Okay? So all that stuff to the left of 3. And then this parenthesis goes right here on 3. How did I know it was a parenthesis and not a bracket? Because of this symbol. So you can see how I color-coded it here. It's a strict inequality, no or equal to. That's what makes it a parenthesis over here. When you graph these in Hawks, there's going to be little arrows under it that you're going to have to click and drag to the right location. For the for the negative infinity, you're going to have to drag it out here in Hawks until it has like a ... That's how you know you've got it. Don't just drag it to like -10 and be like, that's good enough. No, -10 is not close enough to negative infinity. It's not. So, negative infinity, you'll see in our interval notation answer. Look, negative infinity gets a parenthesis. How do you know if it gets a parenthesis or a bracket? Well, positive and negative infinity always get parentheses. That's because they're not numbers that can be included. Okay, the bracket is going to include a number if there's an or equal to. These are not numbers. Okay, negative infinity and positive infinity are not numbers. They are symbols that represent unrestricted growth in either the positive or negative direction. They're not actually numbers. All right, so let's look at another example here. How about x greater than or equal to -1? All right, on a number line, I put 0 there for reference. -1 would be the left of it. Everything greater than or equal to, greater than being bigger. The or equal to is why I'm putting a bracket there and not a parenthesis. So the bracket goes there because of the or equal to here. Now when I write this in interval notation, look, notice how I'm just translating the shaded area into an interval. Look, this shaded area, the far left is -1 and it's got a bracket. The far right is infinity and those always get parentheses. So again, why did I put a bracket here? Follow the color coding here because of the or equal to, which follows my directions from back here, remember? All right, so interval notation is always written smaller, comma, larger. You don't want to write it as infinity, comma, -1. or 3 comma negative infinity. The smaller has to come first and then the larger. So they do go in this kind of numerical order. Okay, how about this one? This is a way of saying all of the numbers that are between -7 and 0, including -7 but not including 0. I say that because of the or equal to here and the strict inequality there. Now, just translating those symbols into our bracket and parenthesis, and knowing that because this x is between those numbers, that it means all the numbers between this. So don't read this exactly as it looks. I hear students who will say, oh, -7 less than or equal to x less than 0. That doesn't make as much sense as if you say, hey, this is all the numbers between -7 and 0. Because that has an or equal to, I'm going to put a bracket. Because that's a strict inequality, I'm going to put a parenthesis. Boom. See how that translates directly to that interval notation? It's beautiful, isn't it? Fantastic. Okay, so that means by that rationale, this example is pretty easy, right? It's all the numbers between 1 and 10. We don't even have to draw a picture of it, do we? We can go straight to the answer. Look, I went ahead and just wrote down the answer, 1 comma 10 with brackets. How am I able to do that so quickly? Well, I know that's between. So there's the left, there's the right number. They're both brackets because they're both or equal to's. This one, x is between -4 and 0. And both of these are going to get parentheses because they're both strict inequality. Now this looks like a point, but given the context of the problem, this is an interval from -4 to 0. Okay, so now that we've got some interval notation, down pat, let's talk about how to find unions and intersections with these interval notation things here. So let's say that set A is the interval from 2 to infinity, and set B is the interval from -10 to 5. Now we say that this one is what's called a half open interval, and this one's a fully open interval, in case you hear Hawks use that terminology. Open meaning that both sides are parentheses. Closed would be that both sides are brackets. If you have one of each, it's called a half open. All right, so let's find the union and the intersection. So just so we have a visual here, I went ahead and graphed both of them on the same number line. So 2 to infinity is a bracket on 2 and then everything over to infinity. -10 to 5 is a parenthesis on both and then everything between there. Now we know the intersection is the overlap, and the union is anything that's shaded in blue or red or both. So the union being anything shaded, well, that's everything from -10 all the way to infinity. Notice there's a parenthesis. So I am using this color very intentionally, okay? I don't want you to look at this color and think I'm just trying to spruce things up here. It is very intentional that this red stuff goes with this red stuff. This blue stuff goes with this blue, goes with that blue right there. The overlap of the two shadings is right here from 2 to 5. And again, you'll notice that bracket and that parenthesis right there. All right, let's go back to that set builder notation here. If P is the set of elements that are less than or equal to 2 and Q is the set of elements that are greater than or equal to 13, let's find the union and the intersection. All right, so just like always, let's graph these on a number line. We know the union is anything shaded and the intersection is the overlap. So everything less than or equal to 2 would be back here. Bigger than or equal to 13 would be up here. Let's do the intersection first. Where does the red and the blue overlap? Well, they don't. So we say that because they don't overlap, the intersection is the empty set. Right? There's nothing in the overlap. There are no numbers that are in both P and Q. The union is anything that's shaded. But this gets kind of tricky, right? Because they're not really connected. So you don't want to write negative infinity to positive infinity because this isn't shaded in red or blue or both. So here's how we have to write it. Because they're disjoint, right? Because they're not connected, you have to write one set and then you're going to put a little union symbol in the other set. You could also write it in set builder notation with the word or between it. Okay? This is really messy to do. That's why I wanted to do an example to show you what would happen if you had to do a union of two sets that don't overlap. Now this this kind of unioning, separate intervals is pretty common practice that you might see a lot more frequently in this course and higher courses if you're going to be taking those. Okay, so let's talk about graphing these. So if we want to graph, this is a union right here because of the word or. So union is or, intersection is and. I'm asking you to graph on the same number line the union of these two sets. So you know the drill, right? That's everything from 5 on. This one's less than or equal to 4, so we get a bracket, and then everything below 4. See, 5 is a strict inequality, so it has a parenthesis. Or equal to gets a bracket. The union is anything that is in one or the other or both. Now these, just like the last example, there's no intersection, right? It's empty. No overlap. When you do this in Hawks, Hawks is going to give you a number line, and then it's going to ask you, like when you go to graph, say this red part over here, when you go to graph this, it's going to ask you which one of these 4 do you want to use. Knowing that infinities always get parentheses, this red would be parenthesis, parenthesis. So you would click on this little button. It would put 2 parentheses on the number line, and then you would click on the arrow underneath and drag it to where you need it. Remembering that when you do the infinity, you have to drag it to where it gives you those 3 dots to let you know that it's all the way over. For this one, that's going to be a parenthesis and a bracket. It matters which one you pick. You'd want to pick this one because it's parenthesis on the left, bracket on the right. If you pick this one, you're not going to be able to drag this parenthesis over this way. Okay? So I just want to point that out when you do these in Hawks. Okay, so this one's going to be an intersection because it says the word and. So or is union, and is intersection. So less than or equal to 2 and greater than or equal to 0. So here's what we're going to do. We're going to graph them on the same number line. Greater than or equal to 0 is going to be a bracket and then everything bigger than 0. Less than or equal to 2 is going to be a bracket and then everything below 2. The overlap is anything shaded in red and blue. So that's that 0 to 2. Bracket, bracket. Now, if it asks you to graph the final answer, the graph of the final answer would be this. So you wouldn't want to graph but all of this together. If it just asks you for the graph of the final answer, it's this one. Oops. Okay, so how about this one? This one's not in set builder notation or inequality notation. This one's in interval notation. So where's the union of these two? Well, let's do like we always have, and let's graph them on the same number line. So negative infinity to 4 is parenthesis on negative infinity, parenthesis on 4, everything between. Bracket, bracket, so bracket on 1, bracket on 7, everything between. The union is anything shaded in red or blue or both. So that's everything from negative infinity to 7. And if you wanted to graph the final answer, it would be this. You wouldn't want to put this stuff in the middle here. This was just my work of showing you how I got that final answer for the union of these two intervals. Okay, so now we are finally ready to solve some inequalities at long last. When it comes to solving inequalities, they are going to solve just like equations, except, now you might remember this if you took Math 90 recently, because we did some of these in Math 90, they're going to solve just like equations, except the last step. If you divide or multiply by a negative number, you're going to flip the direction of the inequality. Okay? So if I start with, say, this, just ignore that scratch off for now. If this was an equation, you would start by subtracting 3 from both sides, and then you would divide by 2. So this is exactly what we're going to do. I'm going to subtract 3 from both sides, so that goes away. So I'm left with 2x is less than 5 minus 3, which is 2. That smushing right there is multiplication, so the opposite is division. I'm going to divide both sides by 2, and I get x is less than 1. Notice my inequality stayed the same direction throughout, because I did not multiply or divide by a negative number. I did subtract, but that doesn't flip the direction. Subtracting a number does not flip the direction. It's only in this last step here, when you divide, that if you have to divide by a negative, then you flip the inequality. All right, so next up here, just like with equations, we're going to solve these by moving those constants to one side, variables to the other, and then dividing. So because that's a positive 14, I subtracted 14 from both sides. I got negative 5x is greater than or equal to negative 10. That's from 4 minus 14. And then because that's multiplication, that's smushing, I divided both sides by negative 5. And you'll see I made a note here. I divided by negative 5, because remember that fraction bar right there means division. That means I have to flip the direction of that inequality. I didn't change it from an or equal to a strict. No, I just flipped the direction of it. Okay. So let's look at another one here. This one's a little messier. We have variables and constants on both sides of this inequality. Just like with equations, we're going to get all the variables to one side, constants to the other, and then divide. So that was a minus, so I'm going to add 2x to both sides. It gives me 8x. Bring all that other stuff down. That's a positive, so I'm going to subtract 5.91 from both sides. 1.11 minus 5.91 gives me negative 4.8. Bring that 8x down, divide both sides by 8. Now remember, if I'm going fast, you have the option to pause and rewind here, okay? I did not flip this inequality at all because I never divided by a negative number. I will point out when I do. All right, next up. So these are just getting a little more complicated, kind of like they did with equations, right? We get these whole multi-step equations. This is good to review those prerequisite sections in Chapter 2, because those review how to solve multi-step equations. So that's where this stuff comes in. I'm going to distribute throughout here. So I distribute those terms, and I'm right back where I was with the previous example. I'm going to move that 3x to the other side, combine those like terms, subtract 15 so that I get those constant like terms together, and then divide both sides by that negative 9. Because I divided by a negative, I flip the direction of that inequality. Okay, this next one is what's called a compound inequality. This one has this variable, and look, it's smushed between, so there's 2 inequalities here. Now these smushing between these things are a piece of cake. You just have to treat it like an equation, but instead of doing things to both sides, you have to do it to all 3. So if you just had this part right over here, you would just subtract 5 from both sides, right? Well, you just have to subtract 5 from all 3 parts. That gives you negative 9. Those zero out. You got x by itself, and then 6 minus 5 is 1. Now, I did write that in interval notation as well, because those are both strict inequalities. Those are both going to be parentheses. Okay. This one, very similar here to the last one. Just a little extra work to have to get that x by itself. Here I'm going to start off by adding 3. That gives me 6. 3, 0 off, so I'm left with 4x. Negative 1 plus 3 is 2. So I just have to add 3 to every one of these regions. Okay? Then I have to divide by 4, but I have to divide every single one of these by 4. So this is 6 over 4, which reduces to 3 halves. 2 over 4 reduces to 1 half, and we know those cancel right there and give me just a 1, which I don't have to write. And I could write this as an interval. Notice how these both have brackets to them because these are both or equal to's. If one had been an or equal to and one had been a strict inequality, then I'd have one bracket, one parenthesis. All right, I know what you're thinking now. You're thinking, is this video almost over? No, you're wondering, I wonder what would happen if I had to flip an inequality with this mess. We're almost done, I promise. I know this is kind of a lengthy video. These sections coming up are kind of long. All right, so here I'm going to subtract 2 because that's a positive 2. Get negative 13. Don't forget this sign. That'll give me negative 22. And then I divide all 3 of these by negative 3. When I do so, I do have to flip the direction of those inequalities. Now, how did this end up positive? Well, because it's a negative divided by a negative. Over here, negative divided by a negative is a positive. Okay. Now, we have some that are not included in Hawks, but are part of our curriculum that we do have to discuss. So, and these can show up on tests, quizzes, or your final. So even though you don't get the practice in Hawks, you do want to go back over these and look over these and maybe rework these from your notes. This one, instead of having that compound inequality where they're all joined, kind of smushed together there, these compound inequalities, we have this separate and going on here, which is an intersection. Now here's the thing. Remember when we had the nice ones where it was like, oh, x is greater than 3 and x is less than 5, and you just had to find the intersections? Well, now you have to solve these first, then find the intersection. So we're just adding some extra layers of work, extra steps to it. So treating these like 2 separate problems. That's why I have this kind of lined in the middle. All right, I'm going to add 3 to both sides, divide by 2, get x greater than 6. Subtract 7. That's a 1 right there. Understood 1 right there. So we divide both sides by negative 1. I'm dividing by a negative, so I got to flip that inequality. And then that's a negative divided by a negative, which is a positive. Now I'm not done. These are just 2 parts. I still have to find the intersection of those. So we must find the region where those overlap. So I graph both of those on the same number line. Greater than 6. So we got a parenthesis and then everything bigger than 6. How did I know it's a parenthesis? Because of the strict inequality. Greater than 5. Parenthesis on 5. Everything bigger. Where do they overlap? Well, they overlap here, everywhere from 6 to infinity, or everywhere greater than 6. Hawks may ask you for the algebraic notation. It may ask you for the interval notation. So I'm just trying to use these interchangeably. All right, last example. I know this has gotten kind of long. Thank you for your continued attention. Hope you're not asleep. I realize that my sweet southern lilt can rock you straight to sleep, and this stuff is so fascinating. It really is, though. This stuff's kind of cool. Okay, same thing. This time we're going to have an or in there. So we just have to solve these 2 separately and then find that union, that smushing them together. All right. Oh my goodness. No, it's not helping you stay awake if I'm yawning. All right, we're going to subtract 3 from both sides. Divide both sides by 4. We get this first interval. Come over here. Add 5 to both sides because that's subtraction right there. We get 8x is less than 8. Divide by 8. No flipping of the inequalities because at no point did we divide by anything that was a negative. Now let's graph these 2 regions, color-coded here for your viewing pleasure, and look for where these 2 are smushed. So less than negative 2 is negative 2 to the left. Less than 1 is 1 to the left. Notice how these are going in numerical order. So like 0 would be like right there, and that would be -1. So if you're just looking at this as a standard number line. Now the union's anything that's shaded in red or blue or both. So anything shaded, well, if I just looked at this in like dog vision, you know, black and white here, then that would be everything from 1 back. That's the interval notation. If you wanted to write it in the algebraic notation, that's what Hawkes calls it. I prefer to call it the inequality notation because it's a lot more descriptive. It'll be everything less than 1. Okay, that was a marathon, wasn't it? Okay, so that concludes section 3.4.